the shape of the corona. But when you get high solar magnetic activity with these sunspots, that disturbs the magnetic field, and it changes the overall shape of the corona. To simplify it, during a period of low sunspot activity, when the sun's magnetic field dominates, you tend to get sort of an elliptical football shape of the corona with very clear polar northern and southern brushes, these very thin hair-like streamers. During sunspot maximum, when you've got lots of sunspots and lots of magnetic fields on the surface of the sun, you get a much more chaotic and round and circular shape to it. And there are people who study the magnetic fields of the sun and try to model what the corona will look like based on a science called magnetohydrodynamics. Very complicated stuff. I certainly don't understand it. But they're able to start to be able to predict a day or two in advance some of the major shapes that will be visible during the corona during the solar eclipse. And that's only been possible in the last 10 years or so. So it's always a surprise what the corona is going to look like, and it's always beautiful. Yes?
Yeah, maybe I missed this in your video, but what are the shock waves that your friends were talking about in the video?
He was talking about these ripples that he could see in the corona through his telescope, produced by one of these red prominences as it's expanding up into the corona and pushing material aside. And that's something you're not normally going to see with the naked eye. You need at least binoculars or small telescope. And you can watch totality with binoculars and a small telescope. The thing is, you have to be very careful because you can't be looking at that without a solar filter before totality. You have to be able to take it off quickly during totality without bumping the telescope. Watch totality, and when the sun starts coming back out again, make sure you've got that filter back on. So that's not something you do at your first eclipse. Binoculars might be as far as you want to push it, so that when it's total, now you can look. And when the sun starts coming out, you'll see that bead of sunlight on the edge of the sun, and you'll know then it's time to take the binoculars down. Last question, in the red shirt.
Okay, we talked a lot about how the moon's distance from the Earth affects time totality, but what is the Earth's distance from the sun? How does that affect it?
I'm sorry, how does the
Earth's distance from the sun, how does that
how does the Earth's distance from the sun affect the eclipse predictions? Well, during the northern hemisphere winter months, the Earth actually reaches what's called perihelion, the closest point to the sun, in early January. So during that time of year, the Earth seems counterintuitive, but the Earth is actually closer to the sun in northern hemisphere winter and further away during northern hemisphere summer. That's because the seasons don't have anything to do with the distance of the sun. They have to do with the tilt of the Earth towards or away from the sun. But in terms of eclipses, it means that during the winter months in the northern hemisphere, the sun appears larger because we're closer, and total solar eclipses are a little less common in the winter months than they are in the summer months, when the sun appears a little bit smaller. So we're talking statistically now. Statistically, you tend to get more total eclipses during the summer months than the winter months, simply because the moon is a little bit smaller in the summer and bigger in the winter.